Okay. Okay, so yeah, so last day we introduced two basically one important concept, okay, and then whatever the things we discussed, those are consequences of that concept. So the main concept which or idea which we discussed last day is mutual information. So it was mutual information, and I said, okay, uh, so the mutual information was like, okay, okay, can you guys hear me?
Yes, sir.
Okay, okay. So so what we discussed, yeah, that the main idea which we introduced last day, which we talked about last day, is like mutual information, which we denoted like this, which we defined it like this way: this x given y by probability of x. Okay, but we denoted it in a different way. But anyway, so ultimately this was the thing, and we said, okay, this many bits. Also, we said, okay, this is the unit. This is this many bits. Okay. And then actually, I did not give any justification why this has to be the definition. But we said that, okay, so whenever we talk about random variables x and y in this course, so we always keep in mind that x denotes the information source and y is, so here if we have a channel, so this is my channel, and so x is here, and so here let's say x, and here let's say y. So x could be like a1, a2, some ak, and y could be like some b1, b2, and some bj. So so the meaning of the channel is that it is a noisy channel, and somebody, the sender is like here, this is sender is sitting here, so the sender wants to send some symbols like a1, a2, ak, some combinations of that. We don't know how many symbols the sender wants to send, but we only know that sender would like to send some of this a1, a2, ak, which constitute the sample space of the random variable x, and there is a random variable y uh, whose sample space is b1, b2, bj. So when some ai is or ak is being sent, then one of these bj's is received. So yeah, that's the main. So this is sender and this is receiver. Okay, so receiver will receive something when something is transmitted by the sender. Now the idea was that so what we define is that suppose initially we defined it like this way. That was the notation x uh, semicolon y. This is important, the notation semicolon y, and then some ak, okay, semicolon bj. So and then we define this to be equal to log of p of x given y ak given bj by p x ak. Okay, and what we mean by this quantity is like the amount it quantifies, and so it is basically a number which is measured in bits. So this many bits of information, okay, is supplied when you know that bj has occurred, okay, for which ak must have been sent or ak must have been transmitted, let's say. So BJ is received when AK was transmitted. Okay, so then how much information is content, how much information is supplied when I say this, then that is how much information does this statement contain. It is measured by this quantity. And we did not give any justification for this, but we said, okay, let us assume this. And we called it the mutual information between X and Y. And then we said, okay, that this is also equal to, you can say, why it is called mutual. So because this is also equal to I, Y, X. So if you just exchange the role of X and Y, then this is the same. So that's why it is called the mutual information. Okay, but one thing to observe is that if, let's say, I mean, in order to justify whether, I mean, why this could be a meaningful definition is like, or why this should be the definition. Let's say one observation is like, okay, if AJ and BJ and AK, they are independent. So I mean, independent means there is no relation between AJ and AK and BJ, or let's say if X and Y, they are independent. Okay, then what happens if AK and BJ are independent? That means what? Px given Y, this is the random variable. So AK given BJ, what will be this one? So okay, anyway, the definition of this is what? Pxy AK BJ divided by Py BJ. So now you see this quantity here, then what will happen? This we discussed last day. Given next this, and this is, let's say, AK BJ, okay, AK BJ. This will be equal to log of this, log of Pxy AK BJ, and then divided by Px AK and PYBJ. Now, what happens if these two are independent, statistically independent, AK, the events X equal to AK and Y equal to BJ? If they're statistically independent, then this actually is equal to this. This is the definition of statistical independence of two events. Here, the events are, so if, let's say, if X equal to AK, and if we consider these two events, if they are mutually independent, then probability of this thing, the denominator is equal to the numerator. Okay, so that means then if you take the log, then this is equal to 0. That means, so if this and this are independent, if they are independent events, then this is equal to 0. So this mutual information is 0. So what does it mean? It means that even if I say that BJ is received, since AK and BJ, they are not correlated, let's say, or they are independent, okay, then I am not supplying any additional information with the statement that BJ is received. Okay, so you can say that this mutual information is 0. So there is no additional information. We could not quantify that. I mean, the amount of information which is supplied when you say BJ has occurred or BJ is received is actually equal to 0. Another thing which you said, important thing which you discussed is like, okay, we are do not consider these bits as bits of information, like it is a measure or helps us like in terms of 0 1s, let's say how many information you can store, something like that. Do not consider this as these bits as this. You just have to consider this as unit. But yeah, in some occasions, I will show today maybe an example where this bits, okay, is exactly equal to the notion of standard bits, okay, which is a measure of, let's say, how many bits you can store in some place, something like that. Okay, that will match, but in general, this has no meaning like this, because this quantity, for example, ix semicolon y, mutual information, this could be negative as well, because because this value, okay, could be less than 1. So uh, so this could be, this log of this could be negative as well. So negative bits, so that has no particular meaning if we say bits is number of something, okay, number of places or whatever it is. So this is the main concept we discussed last day, and we talked about an example, which is, so we gave an example of a channel, which was like which we call a binary symmetric channel. So whenever we talk about these new concepts, at least in the back of our mind, at least we have one example, which is a channel known as a binary symmetric channel. Binary symmetric channel. Yeah. So this is what we discussed, and then we talked about, so from the, so because this is based, this definition is based on this individual um, individual sample points. Okay, we can take an average of this over all possible sample points, and then we call that average mutual information, and we denoted it as, so another concept was average. So it was average mutual information, and this was, see, the notation, this was denoted by this x. This notation has changed from individual sample points to the entire random variable x and y. Okay, so this is just the average in a sense of expectation. So since this is a joint random variable, so we defined it this way. So it is like, let's say sum over x, sum over y. So it was like sum x, sum y, p of xy, and then we had this I sum x, okay, semicolon y. This is what was, so this is the average. Okay, so average mutual information, this is what we discussed, and then we talked about self information. Okay, so we talked about self information. Okay, we talked about self information. So this was defined by the by an observation, actually, by observing the fact that if this value is 1, then what is happened? If this value is 1, okay, if this, that means if you are certain that if bj is received, then definitely, okay, ak was transmitted, if this is known. So so p- so whenever this value is positive, px ak, and then only we define mutual information, of course. Positive means that there is a chance, there's a probability that ak will occur. So that means there is also, so this event is uncertain, but this event may occur. Okay, so then the question was how much uncertainty is there. Okay, we wanted to have a measure also, that what kind, how much uncertainty is there about the occurrence of the sample point ak. Then we said that, okay, if this equals to 1, this numerator, if this is equal to 1, then what happens is, that means when bj is received, then it is certain that ak was transmitted. So that means if that quantity is equal to 1, so then that actually gives us that how much information is being supplied, that means how much uncertain this ak is to occur. And this is what we call, this is what we call the self information. So self information, we define it as like ix, okay, some ak is equal to log of 1 by px ak, or you can just say ix, okay, just self information ix for some input. Okay, x is like log of 1 by px, which is equal to minus log of px. Okay, One important thing to notice here is that, say, this concept cannot be defined. So this is just an observation. Although we'll not discuss about continuous random variables in this course. I mean, we can discuss, but our focus is also on coding theory. So we'll not discuss the continuous random variable case. I mean, unless there is enough time. So the observation is that this cannot be defined. This quantity cannot be defined. This cannot be defined. This cannot be defined when when x is uh, when x is a continuous random variable, because it is individually defined. Continuous random variable. Okay, so this is the we talked about it. Okay, what it means. Okay, by self information, and you can see that there are different books. There are different motivation. Okay, some people will say that this is amount of surprise and so on. And so now here, if you see that if just quantity px, if probability is less, okay, then uncertainty is more. Probability, because log is an increasing function, and then probability is more, then uncertainty is less, which is intuitively correct. Okay, I mean, if we explain this as an amount of surprise, okay, then you can say, okay, I'll be more surprised if that event is very rare, compared to I'll be less surprised, let's say, if the event happens often, or let's say, yeah. So 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 that's why it's sometimes also called the amount of surprise. Amount of surprise. I mean, in different books, the motivation is completely different. I mean, sometimes it is completely different. So, I mean, yeah, this is what it is. Okay, now I'll try to give a meaning of this. Okay, so do not forget that this is then a positive quantity, because px is px is lying between 0 to 1. So it is a positive quantity. Px is, let's say, 0, then we'll assume that to be a 0. But let us say px, when px is bigger than 0, then all it is defined. I mean, there is a chance that then this will occur, then there is an uncertainty. If there is no chance that this will occur, then the probability is 0. Okay, we are not considered. So there is no like uncertainty involved in this. So px equal to 0 and 1 case. Okay, so p x equal to 1 case, it is defined, but there is no surprise. So there is no self information. Now I'll give you an example which will give you know. So because this is bits. Okay, but anyway, again, also this is measured in terms of bits. The unit is bits, but it is not bits in a standard sense. Okay, like in an information storage sense. Okay, yeah, but I'll give you an example where it fits with the amount of information. Okay, is exactly equal to, so ix, which is exactly equal to the number of bits. Okay, which you need to store about store x, let's say. Okay, I'll give you an example. Okay, where it fits exactly with the notion of bits. Okay, so let us consider, this is my example. So let us consider a random variable x information source. Okay, so let us consider the information source of the random variable. Consider the random variable x. Okay, whose sample space is just some 0, 1 to the power, let's say, n. What do you mean by this? So whenever I say x, this is the information source, x here, this is some y, and this is the channel. So if I say this, that means all these are, let's say, a1. So a1 is a sequence of 0, 1, okay, of length n, dot dot dot. An is a sequence of length n. Why I'm giving this example, do not forget that we'll talk about coding also in this course. And not only that, whatever we are defining, these are in terms of Shannon's idea. Okay, Shannon's information theory. Okay, now Shannon said like whenever you have a if you consider an information processing in this kind of a situation, whenever you have a channel and where you have an information source, then you always explain this information source as a random variable, and and you have to digitalize all the sample points a1 a2 n which you want to transmit, let's say. So I mean we can consider example where this a1 a2 an, so here a1 a2 a not in the n but it can be like 2 to the power n here because we are considering all strings of length n. So the sample space contains 2 to the power n elements and that you want to transmit, okay, to the receiver. Okay, then the question is what is so, and now so what is the information, the self information about any x? Okay, but when we say what we said is whenever we consider this x, we also have to consider a probability distribution corresponding to x, and then only we can define information. See, this px has to be known, otherwise we cannot do anything. So this unless we know this px, we cannot say anything about how much information or how much self information is there. So we need to consider a probability distribution, and let us say it is this like equally likely. Okay, so let us assume that. Okay, so let all the inputs or all the sample points here, all the sample points, okay, are equally likely. So when I say equally likely, it means likely that is probability of AI, okay, is equal to 1 by 2 to the power n, because there are 2 to the power n sample points, okay, for 1 2 to the power n. So this is the probability. Okay, so that means occurrence of any AI is same. It is same. Okay. Then if we just define what is, then if we calculate what is self information, then Ix, okay, this will be equal to what? This is minus log of Px, so which is equal to minus log of 1 by 2 to the power n, or you can say 2 to the power minus n, so which is equal to n bits. Now you have a complete idea that you see this is an example where this n bits actually meaning that you want to send a sequence of 0 ones or a binary string of 0 ones of length n, and for which you need n bits of spaces to carry or to store that information. Okay, so intuitively now it is clear that this n bits of self information, okay, is required to specify a sequence of, let's say, n binary digits. Okay, so this is like this is fits. I mean this fits. So here I can just say, so this is just a remark. So which we can say that this example, this fits with uh, with the standard idea. Okay, idea about bits. Okay, so the thing is here you see, I mean this is just an example. Don't consider this is standard. Okay, so this is just an example. For example, if you want to send some symbols and transmit some symbol A1 into some AK, okay, then I don't need to, okay, encode all these symbols using strings, binary strings of fixed length. I don't need to do that. But here the question is, if I do that, okay, and let us assume that I have those many possibilities, those many symbols, okay, those many means the number which is equal to the number of distinct binary strings of length n. Okay, so that means to the power n number of symbols, and I want to code all this symbol using a string of 0 1. Okay, then the question is of length n, let's say, And then this is the amount of information I need, or this is the amount of information I need to store it, which is exactly equal to this many bits of amount of surprise I have. Okay, or self information each sample point has. Okay, so each sample point has this many bits of self information. Okay, this is what I could say. Okay, now let us define something else, and then we gradually define what is called an entropy. Okay, so yeah, so before we define entropy of the corresponding random variable and why this is important, let us first introduce another concept. So we first introduce what is called mutual information. From there, we define what is called average mutual information. Now, from there, we define what is called as self-information. Okay. Now, since we are living in a joint space, okay, the XY space, okay, a joint random variable, okay. So we can also consider. So this is a new concept we are introducing. Let's say, so consider let's say conditional self-information. What it means? Conditional, let's say self information. Why we're introducing this concept? Because we are living in a joint sample space. Okay, so now what do we mean by conditional self information? So we define self information of an input, let's say. Okay, now we're into conditional means what is the self information of an input sample point given the fact occurrence of some particular output. This is what we want to define. So see, whenever we have a random variable, okay, whenever we have a random variable x here, let's say, whenever we have a random variable x, okay, and these are the possible sample points, then we can define self-information. So here, when we talk about conditional self-information, that means our random variable is a conditional random variable. So x given y. So then we'll introduce the definition similar fashion. Okay, so we consider conditional self-information of let's say of an event. Let's say of an event x equal to some ak. Okay, given the fact that some bj has occurred, y equal to some bj has occurred. Okay, as this. So what I'm trying to define is I x given y, and then let's say ak given bj. So this must be equal to then log of 1 by probability of x given y, ak given bj. The same definition will define this. So instead, so same thing as saying x given y, okay, is equal to minus log of p x given y. So this is the definition. Same thing. I just introduced this definition because you will see that this definition has some insight about the quantity of the self information. Okay. So this is my condition. Now see here. So let's say this is some let's say 3. Okay. And recall the definition of Ix. Let's say Ix is there's 2. Let's say this is equation 2. And let's say this is let's say 1. This equation is 1. Then what can we say about 1, 2, and 3? Combining all this three definitions, 1, 2, and 3. What can you say? Then this is just an observation. Then from the following definitions, what can you say? What insights do we have from these definitions? One was what? X given y, which was what? This is log of p x given y by px. This is first definition. It was the first definition. Second definition was ix, which is log 1 by px. Now we have another definition, which is I x given y, which is log of 1 by p x given y. Okay, this is the three thing you see. Now the question is, what is observation? What is the observation from the above definitions? What can you say about these quantities? So these are all mutual information or self information. Okay, in fact, this is the conditional self information. This is conditional self information. This is self information, and this is mutual. Now remember the explanation about all these quantities. Self information, we know what it means. Conditional self information, we just discussed, and this is mutual. Now how this should be related? Now see in the expressions how it is defined. Using this expression, what can we say about that a relationship between all these quantities? Can anybody say this? If you do a little math from the definitions on the right hand side, you can
Yes, sir.
say.
Here we can use a law property here, and we can make explicit, and we can use equation 2 and 3, and can put the equation 1, then we can get result.
So how these three quantities are related? What is the relation? My question is how
Yes,
these three quantities.
so we can write first equation as uh, I x comma y equal to a conditional x minus equal to minus I मतलब information x given y plus ix.
Okay, so basically you are saying this is the conclusion is I, and this is important, I x given y is equal to ix minus I x given y. So what it means? So in terms of explanation, what it means? What does this say? This relation or this equation? So what is this? What is that? And what is this? So left hand side is what? This is the amount of information, okay, which is provided about x, okay, by saying that y has occurred, okay. This is the left side, and it says that this equal to must be the self information which is required to specify x, okay, minus, that means less, ix given y, means this is the uncertainty in that x outcome given y. Do I make any sense? So this left one, okay, let me just write it down. Left one is the amount of information. Amount of information about x, okay, when about the occurrence of x actually when y has occurred. Okay, this is the self information about X. And this is the remaining term, is the amount of information. Okay, about X given Y. And recall, I mean, just note a point here that this is same as this. So, I mean, you can say this as amount of information or amount of uncertainty. That does not matter, because we said uncertainty and this thing, they are just same. Uncertainty about X given Y. Does it make sense, or I need to discuss more about it?
So can you explain that amount of uncertainty about x given y? Why that is a self information of x given
Yeah.
y.
So
So
yeah. So you can say self information of X given Y. Okay, this is what it is. Conditional self information. Okay. Now, self information means what? Self information is highly connected or highly related to uncertainty. You can say this instead of uncertainty, also self information. This conditional self information, no problem. So self information means what? So there is an uncertainty about the occurrence of this. Okay, occurrence of this X. So question is, once you know that X has occurred, okay, how much, so you want to basically quantify how much uncertain this event is, how much uncertain the appearance or the occurrence of this outcome is. And that is provided by, let's say, this is how much is required, self information. Okay, so about a particular outcome, let's say X, or about a particular input, let's say X. Now, next part in the right hand side, Ix given Y, that Y has occurred. Okay, this is conditional, Y has occurred. Then how much self information does X have? So there will be a change after knowing the fact that Y has occurred. Okay, now we are saying that this guy was what? I of this is amount of information that X has happened after Y has occurred. Okay, or X was sent, transmitted when Y was received. Okay, this is nothing but whatever self information you have, and then you take out a part which is the amount of self information when you know that Y has occurred. So self information, then subtract it. I mean, you subtract self information given Y from self information, then whatever amount is there, that is actually amount you need to know that X will occur when Y has occurred, or X is transmitted when Y was received. Is it clear now, or if you have doubt, you can ask me.
so then how can we compare with that I y semicolon x with this I x minus I x given y? Like with
The,
this
this one,
yeah leftmost that
no, this
I
one was okay. You may forget it, but this was by definition it was equal.
no, sir, I understand that, but
Hmm.
if I want to compare that with the rightmost expression, ix minus ix given y,
Hmm.
like,
No, this relation. Okay, if you are confusing, if you this is a confusing thing, let us forget about that. So what I'm trying to say that this is according, this relation does not come from sky, but this is from the definition of mutual information. So everything, all these three quantities, they are related through the definition of mutual information. If we assume that the definition of mutual information is correct, then this is what we get. Now the question is, if this is what we get, we need to also understand what does it mean. Okay, so this follows, this relation or this equation follows from the definition of mutual information. Now we have to understand how this thing, I mean, what is the meaning of this relation? And that is what we are trying to explain. So we have one particular x, which is an input sample point, and one particular y, which is an possible output. Now the question is, so when y has occurred, okay, what about x? This is what we are mm, trying to quantify. Now this relation says this amount of information, okay, which is what? The amount of information about the occurrence of x when y has occurred. Okay, this amount of information. That means when we know that y is supplied, then x will also occur. This information is supplied that y has occurred, then what is the amount of information that x will also occur? This is same as the self information about x. That means self information about x is about, you can assume again the same thing, like the amount of surprise that x has occurred, the amount of information, okay, about occurring of x. This, and then is because we have additional information here that y has occurred, this is same thing as saying that this self information, and then subtract the amount of information or amount of uncertainty or the conditional information when you know that y has occurred. So this is how it is related. I just keep on repeating the meaning of these three quantities, and they are related according to the definition of mutual information this way. And this is the relation how they are related according to the definition. Does it make sense?
Yes, sir. Yes, sir.
Okay, I mean, even if it does not make sense, this is fine. Okay, so gradually we'll understand. Okay, gradually it will understand, because this is this quantity, I mean, all these things are really abstract. Okay, so I mean, so if you believe in that definition, and today I gave you an example of why one can believe. Okay, but gradually it will be unfolded, like it will it will unfold that why this definition is probably correct. But if we assume that definition, then how these things are related, and we are trying to measure something which is amount of information which is not properly defined. But what theory we are doing is, this is according to Shannon, and he said that if you consider the information source as a random variable, then this is how it can be defined. And once this can be defined, then what are the implications? Okay, this is what we are trying to discuss. Okay. Okay, now we'll consider the most important definition, which is, now here you can see, okay, so here is just an observation again. So that self information, okay, self information is also, you can consider it as a random variable. Why it is that? Because, okay, so it is, let's say, a numerical value. You give something some x, so it will have a value, so numerical value. So you may consider this also as a random variable. Okay, just like in mutual information. Then we are trying to now define. Okay, so let us now define what is called the entropy. Okay, now we'll define the entropy of a random variable. Okay, entropy of a random variable. Here it is x, entropy of x, let's say, because it is the information source here in our course. Okay, so this is defined as the average of self information, the average value of self information. So that means what? So it is conventionally, it is denoted as h. Okay, hx, which is then sum. Okay, so this was Ix, and then this should be with the probability x, so it is like this, and whatever x is, so x belongs to, you can say, yeah, overall x. Okay, so according to our notation, so this is something like probability x sum ak, and this is log 1 by px sum ak, and this k is equal to 1 to capital K. So yeah, so this is same thing as saying minus sum of x px log px. So this is the average value of the self information. So what does this entropy mean? Hmm? What does it mean then? See, this x, this amount of surprise, is defined for a particular possible input, and this hx is the average of that. Okay, the self information is defined for a particular input, and hx, the entropy, is the average of that. So if you take the average, means with some probability, okay, x will occur. So with some probability, that self information, you will have that amount of self information. So if you do that, then that is what gives us the entropy. Now, what does entropy mean? Can anybody say something about entropy? What it should mean then? No idea. Hmm. Okay. So I'll just tell you, just think about it. But here I'll just keep a note that later I will give, mm, let's say, I'll give an example, or yeah, I'll give an example. Okay, about the meaning of entropy. P in terms of coding or encoding the the sample points A1, A2, AK. Now note that Shannon said if you want to transmit A1, A2, AK, that means all the inputs, okay, then you have to digitalize it. That means you have to use a string of 0 ones, okay, to transmit, okay, the symbols. You need to define. So if you want to transmit, let's say AI, you need to transmit a sequence of 0 ones, a string of 0 ones corresponding to that AI. So now the question is, how do you define that string of 0 ones, okay, corresponding to a possible input AI? And once you do that, okay, so there must be a mechanism. So then the question is, there can be different mechanisms to define. Then the question will be, what is the optimal way of associating strings of 0 ones or strings of binary digits to each of these possible input for the transmission? Okay, what should be the optimal way of doing it? Okay, so that will be explained. That will be, I'll relate that with the concept of entropy. Okay, I'll relate that with the concept of entropy. But let us say for the time being, the meaning of entropy is the average value of the self information. So average amount of surprise about X, the random inter-random variable X, or average amount of self information is called the entropy. Okay. Okay. Now, since we have defined this entropy, we can define also, let's say, entropy for self information, because this is, you can think of that this is entropy is a random variable. Okay. So we can define each of this. So then we can have another definition. Okay. So then we can say the average info. Okay. So let us, so since we have conditional things, so let's say the entropy, the yeah, the entropy corresponding to entropy corresponding to conditional self information. So we define corresponding to average value of self information. Now we'll define average value of the conditional self information. Then what do I get? Conditional self information. And see here, these are the argument here. Okay, so h is the entropy, h of x. X means the entire random variable. This is because this is about the entire RAM. So this is something, some amount of information, something which is about entire random variable, not about three specific points. So it is the average of all the self information. So the entropy corresponding to conditional self information is defined as, it is denoted as h x given y, let's say. This is the average of that. Average of what? I, let's say x given y. Okay, so this is correspond to the joint random variable. So it is xy over all xy. Okay, and so this is same as saying this is minus sum of xy pxy log of p x given y. And this is also sometimes called average information. Okay, required to uh, it's a average information required to specify, let's say, or required to know or specify x. Okay, when, or any small x, in fact, when because this is average when y is known, because this is the average value. So given any small x, okay, so if you want to specify that what is given the fact that y has occurred or y is received, then what can you say about x? So this is the average information, or this is the amount of information. So now once I introduce this, okay, now next question is from this concepts. Okay, question here is, can we relate? Now see here again, recall that we started with the definition of mutual information. Okay, this is the flow of all the definitions. So we started with mutual information. From there we defined what is called average mutual information. Then we talked about cell information. Okay, then we talked about entropy. Then we talked about average information, which is defined as the entropy of this thing, this random variable x given y. Now, since all these concepts are originated from a single concept, then the question will be, how they're related, all these definitions. So can you relate these quantities? I, x, y, the mutual information about x and y, and h, x given y, which you already defined. Can you relate these two? It was the mutual, and this is the average information. So can you relate now these two from the definition? Let's recall the definition of I x y, h x given y. So can you say anything, any relationship between these two?
Sir, if we expand the formula of mutual information, then we can get some relation.
What is that relation I'm going to do? Can you work it out? And can you tell me what?
So we have to work out some simplification, then we can get.
Yeah. Please go ahead and do that, because we have we finished 1 hour. So now we'll take some rest, maybe 5 minutes gap. So during that time, you just use the definition. Okay, what was IXY? I will ask somebody. What is that? Okay, who is SW? Saurabh, Wag, SW. Who is SW here? Whose name code is SW? Okay, let me find it through ERP, because maybe he switched on and then left. Anybody about the relationship of these two quantities? Okay, Sushant, not Saurabh. Sushant.
Yes, sir.
So why are you silent? I am saying that whose code name is SW, and you are not responding. Why?
No, sir. My name is Sushant. My full name is there, so I thought SW might be someone else.
Okay. Now tell me how
Yes.
these two definitions are related. Because last day during the class, did you mute somebody? Because I forgot
No.
to take the control. Huh? Why did you do that?
No. I didn't mute anybody.
Because in my this thing, it showed your name. That's why I'm asking. You may deny. There is no problem.
Oh, then it might. Then it might happen. It might be my mistake, but I didn't did it intentionally.
Not one time, 15 times maybe, or more than that.
No, sir.
No? Are you sure about that?
Yes, definitely.
Okay. But don't do this kind of mistake next time. Now tell me, what is IXY, what is HX given Y, and how can it be related? What is the definition of IX given Y?
It's log of probability of x given y divided by probability of x.
Okay, good. So x given y, and this is x. Okay. Yeah. And then this is equal to what?
This is equal to
Mm.
negative of summation of
Mm.
p of xy log of p of x given y.
Mm. Okay. Okay. Log of.
P of x given y.
Okay. Maybe I can write this. Okay. So now how to relate this to? Bolo.
Mm,
Okay. So I'll ask this kind of questions in the assignment or in the Viva. Okay. So this is my homework, let's say.
Sir,
Okay.
I got this result.
Ah, tell me,
Sir,
what is that?
sir, this will be h x given y equal to h of x minus I x comma y.
Okay. And this is correct. X, y, the mutual information between x and y will be hx minus h x given y. How do we explain this? Okay, so
Sir,
the
we
yeah.
first we start from the left hand side, and
Hmm.
if you expand this formula and take summation, then we can get right hand side.
No, this is okay. Mathematically, this is the case. Okay, so that's
Yes,
true. Now the question is, now what is its interpretation? How do you interpret this equation or this relation? So how do you interpret from this equation? How do you interpret, let's say, Ix, so mutual information between x and y? So
see the
mutual,
average
uh,
information of mutual information.
no, that is the definition, right? Ix given y, Ix semicolon y. Now the question is, this quantity is equal to this quantity. Question is how? I mean, what is the meaning then? We know the meaning of this whenever we defined it. We know the meaning of each of these terms. The question is, then how do we relate these three things, these three quantities? So what was the mutual information between x and y? This is the average amount of information, or let's say uncertainty, right, between x and y. Or maybe you can say more specifically, when some y is observed, okay, some outcome, or say output small y is observed, then what is the amount of information that some small x will be observed, okay, and then average value of that, okay, for any xy. This is the left hand side quantity, and right hand side quantity is hxy, let's say this guy, hx given y. This is the what, the average conditional mm, self information, okay. So it means so how much about x, okay, average information required to specify x when y is known. Then this three, and hx is the mm, entropy of x. So how this three things can be related? What is the meaning of this? So question is how to interpret it. Okay, this is a question for Viva. Think about it. Okay, now what we'll do is, since all these concepts, all the definitions were initiated or originated from the definition of the mutual information, so we'll now try to find out some more relationships between all the definitions or all the quantities that we introduced. Okay, so another observation. Okay, so if I give you a pair, let's say x and y. Okay, I give you a pair x, I give you a pair x and y. Now if I ask you what is the self information about this xy, why I am asking this question? Let's say self information was defined for a random variable. Okay, h of I of x. Okay, I of x was defined for a random variable. I of x, I of x is defined for a random variable when x is the random variable. And if you know the probability distribution, you can define self-information about x. Now here, I'm talking about self-information of a pair x and y. Then what should be the definition? So what should be this? Because here I have a joint random variable. Then what should be the definition? Chaman Singh, are you here? Chaman Singh?
Yes, sir. Yes, sir.
Bolo. Bolo. Tell me how this can be defined. कैसे डिफाइन कर सकते हैं इसको? हमको क्या पता है? हमको पता है ये सेल्फ इंफॉर्मेशन. Okay, which is
Yes,
this ऐसे. This is
minus
how it
log
was.
px.
Yes. Now what should be the, so this is known. Okay, this is known to me. Now I want to define the self information for a pair xy. What is y?
Joint C.
So how do I define it now?
Think. Sir, minus log px comma y.
Yeah, minus log px comma y. That's correct. Because here I had only one random. So if I want to specifically write this, so this was log p of x and then x. Instead of x here, I have a joint random variable. So I have to write p x y and then xy. Okay, this is the original notation if you want to write it explicitly. Yeah. So if you know this, so I can define this. Now what I want to do, I want to correlate. Okay, I want to relate. This is my next question. Relate the following quantities. One is Ixy, which is self-information about xy. I know about self-information x. I know about self-information I, x given y. Okay, when y is known, then what is the self-information about x? Now, can we relate these three quantities from the definition? I have all the definitions now. Now can we relate all this? So Ixy I just defined. All are this like self-information. Ixy, Ix given y. How can this be related? Anybody? Okay, Benudhar Sahu, are you here?
Sir.
Benudhar, bolo.
Yes, sir.
How these three can be related, bolo? Tell me. Use the definition and tell me how these three are related. Okay, my next question would be, this is this first question. And next question is to Mansi. Mansi Bajaj, are you here? Mansi Bajaj, are you
Yes,
here?
sir.
Yeah. My next question to you, okay, and it would be how to relate I, X, Y. Okay, I, X, I, Y, and I, let's say, I, X given Y, Y given X, all possible quantities. Yeah, how this case can be related. You think about that. So here, the notation, here, this is, so here you see, this is X and semicolon Y. This is X semicolon Y, and this is X comma Y. That means this is self information and this is mutual information. Notational difference. Okay, everything is same except this comma and semicolon. Okay, Benudar, tell me.
Sir,
Can you do that? Use the definitions of all these quantities and tell me.
Ix is equal to
Ix. Okay, go ahead.
is equal to Ix comma Y minus Ix given Y.
No. Okay, let me tell you, and then you verify that this is the correct. So what you said, I'm writing in a different way. So you said X given Y, that has to be actually Y given X. So let me write it this way. X, Y is equal to Ix plus I, Y given X. Now can you prove that? Or this can also be written as I of Y plus I of X given Y. Can you prove this? Mansi, you have anything to say about the next problem? Mansi, can you hear me?
Yes, sir.
What about the relationship between this I, X, the mutual information between X and Y, Ix, the self-information of X, Iy, the self-information of Y, and the self-information of X when Y is given? How can you relate these quantities using the definition only? Can anybody tell me how these are related? You just have to use the definition.
So Ix plus Iy is equal to Ix comma Y plus I.
Okay, I'll tell you.
Sir,
Relation.
second will be equal to Ix comma Y equal to minus Ix given Y plus Ix.
Okay. So I am writing, let's say, a relation. Okay. From that, you can try to write another relation and so on. Okay. So now first tell me whether this is true or not. Is it true? If it is true, then again from the previous relation you can use the previous relation and you can have one more equality, something else. Now is this true? This mutual information of X and Y is
Yes.
equal to hmm? Just use just
Yes, sir.
the
It's true.
formula.
Yes.
Is true. Okay. My next question is, since these are all the individual quantities, like for a pair of, let's say, input and output. So instead of that, we can take the average values of all this, both sides, like sum of xy, then pxy, whatever it is, okay, based on whatever the corresponding random variable is, okay. If we do that, so what can we say? My next relationship is this. Now, can you prove that? My next relation is h xy is equal to hx plus h y given x. You will see these are all big theorems in the books, okay, but these can be proved easily from all the definition itself, and this need not be theorem, just homework. Okay, now can anybody, suppose I want to prove this. Now can anybody tell me what is this quantity? Can anybody tell me? Can anybody tell me? Oh, sorry. Can anybody tell me what is the quantity in the left? What is this? How do you define this? Or what should be the meaning of this? Okay, or maybe you can find out this because this already I defined. Using this, what is the thing you get which can be called as this? Hx, you already know, right? Hx is the entropy. Hx is here. Yeah, this is Hx, entropy. And Hx given y is a conditional entropy or conditional cell information, okay? Or average information record, whatever it is, okay? You know this definition. You know this definition, okay? Using this two, if we just add them up, what do we get? X given y, so you have to add this quantity with h of y. Otherwise, you can just write h y given x and you have to add it with hx. Then what do we get? Or maybe does anybody have any idea how this should be defined? The left-hand side. How the left-hand side should be defined? H of xy. Because see, xy here I'm writing as a joint random variable. Now, since I defined entropy of a random variable, right? So I can define also entropy of a joint random variable because it is also a random variable. The same thing. So instead of px, it will be just pxy. Whatever the formula is, same formula. My question is, all these are obtained from this h thing is obtained as average value, okay, corresponding to something like self-information, average self-information. So now since we have this relationships here, like 1, 2, using this 1, 2, taking the average, both sides, something like that, can we prove this one, the third one? And if we prove the third one, what is its meaning? Can anybody do this? What is the entropy of a joint random variable? That has to be equal to the entropy of x plus entropy of the conditional random variable y given x. So according to Shannon, entropy is amount of uncertainty, okay, about the random variable, let's say. Okay, let me ask somebody then. Samaras Jina, are you here? Samaresh?
Yes, sir.
Yeah, can you tell me what is going on here? Hxy, hx, and hy given x, how these are related using the relations above. First tell me how hxy should be defined. The left quantity hxy, how it should be defined. Hmm? How should it be defined? Okay, Priya Sharma. Priya Sharma, are you here?
Yes,
Tell me.
it's entropy of X and Y.
X and Y? What do you mean by that?
It's like multiplication, like we do in probability to find the probability.
So X, Y is multiplication of X and Y. What do you mean by that? Probability multiplication. I mean, what is
Not
the, so how it is defined? Okay, Vandana, are you here? Vandana Prabhu, are you here? So it's not here. Ritvik Singh Roy, are you here? Hmm. He is also not here. So what I'll do is I'll take the attendance now. Whoever is here, based on that, I'll give this. Ritik Shingorai, are you here? No. Okay, then Osho, are you here? Osho Bhogana? Gautam, bolo.
Hello? Yes, sir.
Bolo.
So it
What is
is
the
expectation of joint distribution of x and y. Of like we can define as x comma y equal to double summation x y probability of x comma y into h of x comma y.
Okay, then if that is the case, then how are these related? How are these things related? I'm giving you a hint. The hint is
We can change
bolo.
joint distribution. So we can change joint probability distribution in conditional form, and after applying summation, we can get first result.
Okay, so I'm just writing take average. Okay, both sides of the expressions or the relation. Okay, because these relations are defined for individual x and y. But when you are defining for capital X and capital Y, you have to take the average. Okay, this is the idea. So yeah, of 1, and take what happens if you take the average. This is the hint. Okay. My next homework is this. Is I X given Y. See, I will ask this kind of questions in the Viva. And Viva will consider, I'll consider a great weightage for that. Okay.
Sir, what was the relation one?
This relation 1 here. This relation.
Oh,
So,
okay,
or
sir.
expression. Okay, relation or expression, you can say. Whatever it is. Relation or expression. Okay. My next question is, you have to prove that this is the case. Age XY. How do you do that? So now see here, since Ix, so this is the average mutual information, right? The average. And there is here, you see the average. So the idea is same thing. Hint. Hint is take the average. Okay. Take the average in the second relation. Okay. Hint is take average and the average values. In the relation or the expression. Expression 2. Okay. Now, whatever we have done, see, still now, we only have done for 2 random variables, x and y, where x is the input, y is the output. You have, let's say, a channel which relates this. Okay. So y is the output corresponding to the x's, input x. This is what you have. But these all can be extended, okay, to n number of random variables like x1, x2, xn. And in that case, okay, in that case, the idea is that instead of one channel, you have multiple channels cascaded together. Meaning, let's say you have something like x1 here, and then you have the first channel, then x2 here, then you have the next channel, okay, some x3 here, and so on. Then the question will be, so let's say this is Cn minus 1 or Cn. What will be the Cn minus 1 or Cn? How many channels will be there? N channels or n minus 1 channels? Can anybody
N
tell
minus
me?
1.
N minus 1.
N
Yeah,
minus 1.
n minus 1 channel. Yes. So then what happens is now, this is now a terrible situation here. Okay. Why? Because then the question is, for example, if I ask how the output in x3 for which the input is x2, okay, how's the output in x3 are related, or the output of the channel C2 are related to the input of C1. Output of C1 depends on the input of x1. Output of C2 depends on the input of x2. So ultimately we can say that output of C2 depends on the input of C1. The question is, how would they be related? So if I want to consider this kind of a channel, okay, where somebody is transmitting information from one station to another station, then from that station to other station, and so on. If this is how the information is being transmitted, then the question is, how can we define mutual information between some random variables, okay, when something else is given. Okay, something else has occurred, or maybe conditional mutual information, okay, between two random variables when something else is defined. Okay, we can define all this, and then we can again take the average conditional mutual information, and again we can have several kind of relationships like this. Instead of two, I'll have n number of random variables, and accordingly they will be related in different ways. Okay, so let me just mention about a few joint random variables, of like n random variables, joint n random variables, and how we can define concepts like this. Okay, so I mean, when I'm writing that x1 x2 dot 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 xn as a joint random variable, let's say this is capital X, or sometimes, because it is now, you can see it is a random vector. Okay, and earlier when you talked about pair of random variables, this is a random vector having having dimension 2, but here it is dimension n. So sometimes we write it that to be x, or some bar x instead of to mean that it is a vector. Okay, and then what are the outputs? I mean, what are the sample points here? We can say the sample points are like x1, x2 dot 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 xn. So let's say these are the sample points. So small x1, small x2, small xn. These are the sample points corresponding to this random vector x. Okay, so basically the sample space of x bar is basically this, all this n tuples x1, x2 dot 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 xn. Okay, such that xi is the same s by, let's say, is an si, where si is a sample space of xi. Okay, where, so I can just say, yeah, where si is the sample space of xi. I can define it this way. Okay, now the question is, can we define all the mutual information, this and that? Mutual information, say always mutual information is defined between two random variables. Okay, because it is mutual. Okay, it is not like a joint thing. Okay, of many more. Okay, it's only between two. And the question is, can we define, let's say, okay, by the way, whenever I am saying that this is just a prototype. Okay, prototype means it need not be the case like when x1 is at the first place, x to the second place, x to the same. It is just a notation. Okay, I mean, x1 could be here, x3 can be, this can be written as x3, this can be written as x2, doesn't matter. I am giving an example, so it means it is like this, but I can say xy, x2, x3 are any random variables, and then I can define the corresponding, what is called, the corresponding mutual distribution and so on. Okay, so whenever I said, like, let's say, okay, so instead of writing, let's say, n, let's say instead of two random variables, we have three random variables. Okay, so let us say, okay, let us first consider example. So let us say, let x, y, and z, okay, be a joint random variable. So a joint random variable. Then my question is, can we define this I, x, y, given z? How can we define this? So what is this? This is the conditional mutual information. Conditional mutual information. For example, here x, y, z could be like x1, x3, x2. Given that x2, or given that some x3, what is the mutual information between x1 and x2? Okay, so how it should be defined? Because this is again a random variable, so we should follow the same definition. So what should be the definition here? It is just a conditional random variable. Okay, so what should be the definition? Okay, yeah, go ahead, anybody? Okay, if we forget about Z, this part, if we forget about this, what was the definition? What was the definition?
Log of
Hmm.
px given y upon px.
Okay, log of P x y, right?
X given y
X given y. Okay, and this
upon
is
px.
Px. Now see, we have everything else here, okay, except the fact that Z is given. That means we have to additionally here we have to write Z. That's it. This is what it means. Because it is the same random variable. Only thing is that here I am defining under certain conditions that Z has happened or Z, the random variable Z is given. Then what is the mutual information between X and Y? So whatever definition I had, on top of that, I have additional information that Z has happened. So I am writing Z, small z here. Okay, everywhere. So that's my definition. Any confusion about this?
Sir, when we are writing capital X, capital Y, that was average mutual information. So, shouldn't
Oh,
we
sorry,
use
sorry.
summation?
Yeah. Sorry. This will be all small. I have to take average, then only I can write capital. Yes, you're correct. Yep. I have to write it like X, Y, given Z. Yeah. Now the thing is, what is that equal to? Can we write this to be equal to this? I, X given Y, X given Z minus I, X given Y and Z. This is comma. Can I write this? Isn't the definition of mutual information between XZ and X, Y, and Z? I mean the conditional mutual information. Can I write this? You just use the definition here. You just use the definition here. Calculate it. You'll see that you'll get back this. But here it is now. It is in this expression. You have now some meaning. The mutual information between X and Y given Z is equal to the self information of X given Z minus the self information of X given Y and Z. Okay. Here, see, there are two things. One is, again, I'm saying this, that we, or every definition, whatever all the concepts we are defining, all are originated from one definition of mutual information. Okay. Now, so if we assume that mutual information definition is correct, then all this will follow. So whatever concept we have defined, now we are just relating those, that how these concepts are related. Okay, this is what we are doing now. So here, if you just write the expression of self, you just write define the self information, the formula for self information of X, conditional self information. Okay, X given Z and X given Y and Z. Then you'll see that this is what it follows. So this is also homework. This is homework. Okay, now since we have this expression for small x, small y, small z, then we can take the average one also. Okay, then taking the average, okay, uh, both sides. Okay, average value of the above information, about the above expression. Okay, what do I get? This can be called as average conditional mutual information, right? So what do we get? What I'm supposed to get is the following, and then you tell me whether it's true or not. I, average mutual information, x1, x given y, z, this will be equal to, what should be the definition here? This is average. Okay, if I want to take the average, then what should be the definition here? Average on what? Yeah, tell me. Here, instead of two random
So
variables, I have three random
Summation
variables.
x, y, z.
Yeah, p of xyz. Yeah,
We have to take
p of,
summation over x, y, z.
okay, summation over xyz, and then times what?
Then log of p of x
Times,
given y.
yeah, so I
Yeah,
x
I.
given, yeah,
Yeah.
y given z. Okay, now we can write, because we already know the expression from the above. Okay, we can write the expression from here. So then the expression is here. Okay, so I can just say that the expression, this expression follows from here. Whatever the expression, I can write that. So if you write it, then you will see, this is homework. This will be h x given g minus h x given yz. Okay, so this is homework. So this is the entropy of x, conditional entropy of, or entropy of the conditional random variable x given z, and this is the conditional entropy of the conditional random variable x given y and z. Okay, so this is one kind of a relationship which you will get, and I can define actually many of these relationships. Okay, I mean, if you just open any book or any exercise of any in chapter, the books I referred to, you will find so many relationships which you can actually find between all the quantities that I defined. Okay, so I'll just maybe note down some of the relationships, and you may try to prove that. If you get stuck, you can ask me, but yeah, maybe we'll conduct a tutorial class or something. But these are all simple, like using the definitions. Yeah, somebody has any question? Yeah, please go ahead. Okay, so another homework is one. You can prove that homework. Another homework is the following: that if I take, I mean, this is for the n case. You have m random variable I x, let's say x1, x2, some xn. Okay, so what is this x1, x2, xn? It is the self information of the tuple x1, x2, xn. That can be proved to be equal to, instead of using other conditional self information, this can be proved, but it has very interesting meaning, by the way. This plus I x2 given x1 plus plus I xn given x1, x2, xn minus 1. Does anybody have an idea how to prove it? Proof is very, very simple. I mean, just looking at the right hand side, expression in the right hand side, you can tell me. Does anybody have any idea how to prove this?
So I think by induction method.
By induction. Okay. So I'll give you a hint. My hint is, so that's why I said you should review your probability concepts. So there is something called chain rule of probability. Chain rule of probability. If you have a joint distribution, P of this, P of, let's say, x1, x2, xn, and this is always P x1. You can prove that, okay? You're just using the definition of probability, conditional probability. x2 given x1, probability of xn given x1, x2, xn minus 1. This is very simple to prove, just using the definition of conditional probability, xn minus 1. Okay, using this rule, you can prove this one. This one, using this, you can prove this one. Let me give you another homework. Another homework is the following. So whatever, since we have this equation is like, I mean, this relation is like with individual inputs, so we can take again an average of that, and then we can prove that this is what happens. Okay, so H of some x1, x2, the joint entropy of this joint random variable, the random vector, you can say. Okay, this will be equal to, I mean, okay, let me finish this. X1 plus entropy of x2 given x1 plus dot dot dot, okay, plus H xn given x1 x2 dot 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 xn minus 1. See, I'm telling this thing again to you. These are very simple. It looks very complicated. These are very simple. Just using the definition, you can prove it. Okay, just use the definition, then you can prove it. Okay, yeah, and yeah, these are the things which I think. In fact, okay, these I already gave you. Okay. Okay. Yeah, this is also homework. I mean, in the books, you'll find all the proofs. Okay. I mean, but these are very simple things. So I'm not proving this because it is, I mean, there is a lot of time to prove this, but, and the proofs are not like very tricky. They follow, the proofs follow the definition itself. So yeah. And yeah, so this is where I stop here today. And next, what we'll do, so the main concern here is, we just said about, let's say today, the main concept to define is entropy. Okay, entropy of random variable. So you can have a single random variable, you can have a pair of random variables, you can have a random vector. Okay, and everything is defined in terms of mutual information. So if we assume the definition of mutual information is correct, all this will follow. And from all these relationships, you will find that how these quantities are related. Okay, and once you find how all these quantities are related, then probably you will understand why the definition of mutual information was correct. Because if you understand what is the amount of uncertainty, what is the amount of information, okay, is defined for a particular random variable, and all these are properly defined, like all the conditional mutual informations and entropy and other things, average mutual information, so many things, then gradually you think that this original definition of mutual information was correct. So that's why I started with mutual information. I didn't start with entropy of a random variable. If you start with entropy of a random variable, you have a very big assumption, hypothesis. But I give you a workable definition of mutual information, and from there, I derive everything. Now the question is, if you have an information source, okay, and suppose something is like defined like entropy, is defined any quantity you define, okay, can I give some bounds about this entropy of a random variable? Because entropy now depends on the probability distribution. Now, using the probability distribution or without using the probability distribution, can we give some bounds about entropy and other things, which will be used actually when we do coding? We'll start coding maybe in the next week, because these two concepts are very related, the information and coding. So we'll do information, then coding, then information, and so on. So back and through will go like this. So then you'll see all these definitions, what I'm doing. Because whenever I said, I'll give you a workable example with entropy using the coding theory, I mean, whenever I will introduce coding, then you will see what is the meaning of entropy when it comes to transmitting information. Because when you want to transmit, you need to code all these symbols. And there you will see what is the meaning of entropy actually. Okay. And here what we did is, it is based on only random variables. And there will have a situation where you are some information processing is happening. Yeah. And Japanjot, are you here? Okay, no, he's not here. Okay, okay, guys. So I'll stop here today. If you have any question, you can ask me.
Sir, in this course we will discuss only discrete random variable.
Yes, continuous we can do when, I mean, if time permits, then we'll do as continuous. For example, you say the means self information is not defined, okay, for continuous random variable because individually this is not defined continuous random. So there are little, I mean, there are things which is little different from discrete, okay, and otherwise all the concepts are almost similar, except a few things. So I'll do that if time permits, okay. So I'll do that towards end if time permits. Otherwise, I will focus only on discrete random variable. It is not difficult, but it's little different. I mean, little, I would say more abstract. Okay. And information is a subject, information theory, coding. This is the science, topic of mathematics, physics, and computer science. Why physics? Because information, whenever you say, I didn't discuss this, but in thermodynamics, if you read any book on statistical mechanics, you will see in thermodynamics how people define statistical thermodynamics, how people define entropy and how it is related with this. But the concept there is much more harder than this concept of entropy. So, so sometimes what happens is some people would say that information is physical. Okay, now you are measuring a physical quantity here. So that's why you need a lot of mathematics to make it workable. Yeah, so I'll do continuous random variables if time permits. Because there are many things, I'll decide that. Yeah. Anything else?
Sir, do we need to know basics of finite field, ring theory, and all those things?
Oh, yeah. I think Japanjot asked this question. The thing is, we'll definitely need to know what are groups, okay? But even if you don't know, you have forgotten, I'll ask you to review that. The basics of group theory will be definitely required, and basics of finite field, at least the definition and what it means, okay? Because we will be working with finite vector spaces, okay? Vector spaces needs the concept of groups and field, okay? I mean finite groups and finite fields. So automatically there's those concepts are there. In fact, we will also, maybe if time permits, we'll also talk about cyclic groups, for example. I mean cyclic coding. So we'll talk about cyclic groups and other things. So it depends how much we can go, but these are all required. I mean, at least one should know all these things. So finite group, finite field, yeah, at least cyclic groups, subgroups, this kind of stuff. All the undergraduate level stuff. Yeah.
Okay.
Yeah. Anything else? Okay, no. So let us stop here then. I'll stop the recording.